with a strange looking initial condition. Now the initial condition, after some expansion could actually be resolved in this form. We could write it, in the standard quadratic form, ax squared plus bx plus c is equal to 0. All right, it's definitely clear that that could eventually happen, right? Because you could expand this, you still have a quadratic, you expand this, you still have a quadratic, collect like terms, bring the 132 over. You could get it in this form, but as you can see, the a's, the b's, and probably the c's would be 4-digit numbers. So you could use the quadratic formula, get a solution, get two solutions, and then plug either of them into this expression and evaluate it. However, there is a much, much better way to do it, and a lot of you probably already see it. If you'll notice, this is already in the form. What we're looking for, if you just examine this, you can recognize that it's in the form a squared minus b squared. And y'all, I'm leaving the squares off of here because literally your a is the parenthetical quantity here, 73x minus 36, and your b is the parenthetical quantity, 19x plus 42. And notice that's equal to, it's equal to this constant, but it's also equal to the very well-known a plus b times a minus b. A plus b times a minus b. Perhaps the most popular identity in all of mathematics, that or either the binomial squared. So you have a plus b times a minus b. Okay, now, so you see, really that's all that's going on in the problem, because if you take a look at the expression we're supposed to evaluate, this expression right here, notice that this would be, with these choices of a and b up here, this would be a plus b right here. Get a little more space here. A plus b. A plus b right here, and then a minus b here. Again, folks, I didn't write it completely out, but I think you could see. Okay, in other words, if a is 73x minus 36, 73x plus 19x gives you the 92 you see right here. Then minus 36 plus 42 gives you the plus 6 you see right here. In a similar fashion, this would give you a minus b, right? 73x minus 19 is 54x, and minus 36 minus 42 is minus 78. Okay, so we see that, again, this a plus b times a minus b is equal to 132, so this is equal to 11 over 132. And again, folks, you can see if you take this to be your a and this be your b, this is a squared minus b squared, but it's given that that's equal to 132 at the beginning of the problem, right? Okay, but when we write it as the difference of two squares, we see we get exactly the denominator of what we're trying to evaluate. Okay, so that's it's designed to work. It's a concocted problem, as many are. But notice that this is equal to 11 times 12, right? 132 is 11 times 12. And so this just ends up, the 11 certainly cancel, and you get 1/12 as your final answer. To me, that's just, it's pretty amazing. Now, again, these are always designed to work out nicely, so it seems amazing, but they're all kind of reverse engineered. Most of these problems that everybody says, oh, you got to be creative, or it's just somebody who's worked the problem. And like before, I've said this many times, you start out on one side and create a problem, All right, and then you present the other side as the problem. It's kind of reverse engineering, but in any event, this entire expression does evaluate to 1/12, and I hope you enjoyed that one.